This is the second video on the topic electrolysis, and here we'll be starting off by discussing the difference between ionization and dissociation. So ionization, you would have done it in the earlier chapters as well. It's basically when a non-ionic compound, that is either a coordinate bond or a covalent bond, any one of those compounds which have those bonds, they break up in order to give positive or negative, any one of them, any charged particles which are called ions. So ionization, we could take the example as HCl. HCl is a covalent bond. It's been discussed, I think, in the bonding chapter as well. So when this breaks up and gives us two positively or negatively charged ions, which in this case are H plus and Cl minus, this process is called ionization. So something which was not already in the ionic state, this is in the covalent state, this breaks up in and gives us ions. So that's ionization. Now the other term is dissociation, which you'll be hearing a lot in this chapter. Dissociation is when an ionic compound or any compound which has an ionic bond, it breaks up and gives its composite ions. So the most common example is NaCl. NaCl will break up to give Na plus and Cl minus. Difference here is that NaCl is already an ionic compound. It has an electrovalent or ionic bond. If you don't remember that, then you should probably see the bonding videos. But that's all the difference you need to know for now. Another thing is that electrolysis is always a redox reaction. Redox is made up of two words, reduction and oxidation. Again, you would have come across these before. Oxidation and oxidation is when an element loses electrons. This is loses over here, and this is gains over here. Combine these two words to get redox. So a redox reaction is when is one in which there is reduction and oxidation going on simultaneously. So you could have two elements or two compounds, um, and at least one of them is getting reduced, at least one of them is getting oxidized. So that is redox. Now, from the last video, you'd remember that in electrolysis, let's take the example of NaCl again. It's the easiest one. So say you have the cathode here. Cathode is connected to the negative terminal. Positive terminal here is anode. So the Na plus ions in this electrolyte will migrate towards the cathode. And why is that? It's because they have a positive charge here. So in order to go back to Na, they need to gain one electron, and the cathode is connected to the negative terminal over here. Meanwhile, the Cl minus ions will want to do the same thing, except they want to lose that one electron. So they're going to go to the anode, which is connected to the positive terminal. So you can see here, oxidation is loss of electrons. That's definitely taking place here. Gain of electrons is also taking place here. So we can confirm that electrolysis as a reaction is a redox reaction. Now the cathode is a reducing electrode, because you could see reduction is gain of electrons. Now Na plus has a positive charge, so it needs to gain an electron, and so it gets reduced. It gets reduced by the cathode. Cl minus, on the other hand, gets oxidized by the anode. If you can't remember this, and get confused with the whole positive, negative, cathode, anode, cation, anion thing, just try to make a diagram of cathode, anode, figure out which one is connected to negative, which one is connected to positive, and I think you would have learned, your teachers may have told you, or in the earlier tutorials, you would have come across oil rig, which is, it stands for oxidation is loss, reduction is gain. Alright, so you could just write this down and just relate which one is losing electrons, so which one is getting oxidized, therefore which electrode is the one that oxidizes or reduces elements or ions. So that's it for redox reaction. Now the next part of the chapter deals with the difference between a conductor and an electrolyte. So conductors, I think physics, you would have done it, class 6, 7. So conductors are, it's basically any metal or any object that allows the flow of electricity through it. So, and these are always in solid state. Now whenever current passes through a conductor, you can take an example of just say any metal piece. Let's do that with a different color. Say you have a metal piece over here and you pass electricity through it. This is a wire here, you've connected it to a battery and you're passing current through it. So say you leave it on for a few hours, what what changes will you see in the metal? um, Now you won't see any major change. If the amount of current passing is a lot, you will probably see that it's hot, and so it might melt. That depends on its melting point, but other than that you won't see any radical change, like it changes color or it changes state, nothing like that. So it is a physical change. So it's a physical change over here, physical. So now in this, any metal will have free electrons. Let's take um, say sodium again. So sodium has one free electron, right? So this one free electron is the one that's going to carry the current through this metal piece. And if you take something that does not have this free ion, it will not conduct electricity. But on the other hand, now if you take an electrolyte, the first difference is that electrolytes are almost never solid. They're only uh, in the molten state or in the aqueous state. So that's the first difference. They're either aqueous or molten, never solid. Um, now, now we've read about how electrolysis works, how the electrolyte dissociates into ions. So it's clear from that um, this is a chemical change. A chemical change takes place when you pass current through an electrolyte because it breaks up into ions. Easy way to remember it. You study conductors under electricity in physics, so it's a physical change, and you study electrolysis under chemistry. And third difference is that we told you in the first section that the current flows through the electrolyte because of these ions over here. These are the ones that conduct the electricity. So over here it is the ions that conduct the electricity, while here it is the free electrons. It's free electrons. So that's it. And the last thing in this section I'm going to cover is just one example of electrolysis, and that is lead bromide, PbBr2. So let me make some space here. So PbBr2, that's the formula for lead bromide. Now Another thing you need to know is about electrodes. Electrodes are of two types. One is attackable and the other is uh, they're not attackable. So in this case we're going to be using non-attackable or inert electrodes. What that means is that the electrodes will be made of an element which does not react with the elements in the electrolyte. In attackable electrodes, we'll come to that later in the chapter, you'll see that the electrode will also participate in the electrolytic reaction, but you should leave that for now. So an example of inert electrodes is graphite. So I'm just going to draw the cathode and anode, the two electrodes over here, and we're taking molten lead bromide over here, PbBr2. Ionic bond, remember, Pb is a metal, Br is a non-metal, so there'll be a strong ionic bond. Now all this, in order for the electrolysis to take place, this whole apparatus needs to be heated. So you provide an external heat source under this. I'm just drawing a flame. I know it doesn't look like one, but it's better than showing nothing here. So it's being heated at temperatures of between I think 350 and 400. So electrodes, I've told you, are of graphite, so they will not take part in this whole reaction. Now once you pass current, we're going to draw the cathode here, so negative, anode here, positive. Okay, so PbBr2. Now you can see that the ions over here, it will break up, and you should notice a reversible sign. This means that the reactants that the products that you get, they can be easily converted back into this form over here. So the products formed will be the two ions, that's Pb2 plus, that's a cation, and the anion will be 2Br minus. Notice the 2Br minus, we need to balance the charge over here. So for every Pb you give out, there'll be 2 Brs that come out. So you can look at the chemical formula over here, 1 Pb and there's 2 Brs, and automatically this charge is balanced. So you have 2 pluses and you have 1 minus in each Br, and you have 2 of them, so you have again 2 minuses, so your charge is balanced. Now the Pbs will go to the cathode, and they'll get discharged over there. What they'll do is accept electrons so that they become go back to their state of Pb. So Pb plus 2e will give us Pb, and these bromide ions will go towards the anode. So Br minus, and they will lose an electron. Br minus minus E will give you just Br. Now you'll have many Pb ions on the cathode, you'll have many Br ions on the anode. Now Br is a diatomic gas, which means that 2 Br atoms, Br2 that is, will make up one molecule of the gas, that is, it's a gas. So once you have these Br atoms, they all will combine amongst each other, form pairs, and become Br2, and Br2 is a gas, so you denote it like this, while Pb will just get deposited on the cathode. Now observations. The one thing you'll observe is that this cathode over here, this will start to become silvery white, and that's only because this Pb here will start getting deposited on the cathode, and it is silvery white. So your cathode will indicate the presence of these atoms by becoming this color. The other observation would be Br2. It'll be released at the anode, and the color of Br2 vapors is reddish brown. So it's like the same as NO2, reddish brown. Now you should remember that. Just gonna write this first. Remember that at the beginning we said the temperatures are very high. You have this heating source over here. So obviously the temperature in this electrolytic cell, you could call it, is very high, and this temperature is definitely above the vaporization temperature, or the boiling point of bromine. The temperature is way above that. So at room temperature, bromine is a liquid. Bromine is a liquid, but when the temperature increases to a certain point, no need to know the value, but over here it will form its gas in its gaseous state. So you'll see vapors coming out like this. So this will be how we're going to discuss all the other electrolytic reactions in your syllabus. So, and for most of them there'll be a distinct observation which will be based on which atom is getting deposited at the cathode, which one is getting discharged at the anode, and so on. So I'm out of time now. I'm gonna carry this on in the next video.